So we just talked a bit about shared memory. The next thing that I want to talk about is the problems that we start to run into once we have shared memory. In order to illustrate this issue, we're going to start off with this program. So we're going to loop through the numbers from 1 to 1 less than a billion and add up the values that are divisible by 101. This seems sort of like an arbitrary thing to do, but it turns out to be useful for this example. So we've got our sum variable, we're adding numbers into it, and we're going to print out the result. Let me go ahead and compile that. Then we're going to get a program called Sequential sum 101. I'm going to run it, and I'm going to run it with the time command so we can see how long it takes. So we're summing the numbers divisible by 101 from 0 to 1 less than a billion. Here's the sum. It's a pretty big number, but it's also a pretty recognizable number. It's all 4 9s, 5s, and 0s. We can see that on my particular computer, that took 2.6 seconds. That's not a super long time, but for a computer program, it's a pretty long time. We had to do a loop, going through a billion things, and do some additions. All right, so let's see if we can speed this up by taking advantage of multiple processes. So I'm going to go ahead and copy seq sum101.c over to proc sum101.c. And then we are going to go ahead and we're going to pull that in here. Then we're going to say const long npp is going to be top over 10. And the reason we're doing that is because we're going to do this with 10 worker processes running in parallel. And those 10 worker processes running in parallel are each going to look at 1/10 of the numbers, so NPP numbers of 100 million. It's going to each worker process is going to check if each of its numbers are divisible by 101, and then we're going to add those together into a shared sum value. To do that, we need to make sum a piece of shared memory. So we're going to go ahead and take every instance of sum, turn it into a pointer. Sum shows up a couple of times. We're going to actually mmap it. So we're going to mmap one page, but we're going to request 8 bytes. We're going to go ahead and say that that region of memory is readable and writable. It's going to be shared memory that's not backed by any file. And then when we're done, we're going to go ahead and munmap it. All right, now we have some shared memory, which means that we can go ahead and try to access that from multiple processes at the same time. For that, we're going to need some more headers. We're going to include that one for mmap. We're going to include that for some reason. We're going to be calling fork and wait. So we need those ones. So for our 10 child processes, our 10 workers, in systems apparently we always have child labor. That's just a good plan, at least if we're going to do parallel execution to take advantage of multiple processor cores. So we're going to create an array of 10 process IDs. We're going to loop through, and then if fork returns a true value, then we know we're in the parent process. So we don't have any work to do. Children do work, not parents. And then in the child, we're going to do that work. Alright, so then in each child we're going to range from some initial value I0 to some maximum value IN. Now I0 for the first process is going to be 0. For the second process it's going to be NPP. So first process starts at 0, second process starts at 100 million, third process starts at 200 million. So actually we want the process number times the number of values to deal with per process. And then IN is going to be I0 plus NPP, because each process is going to process NPP items. So then if we're divisible by 101, we're going to add our value into sum. Then we want to go ahead and exit the child process so that the parent process knows that it's done, and we need to unmap before we exit just to make sure that we've cleaned up. Next thing, in the parent process, we want to go ahead and wait for all the children to be done. So we're going to say wait. And there's our multi-process program that should be able to do the same work as the sequential program, just we should be able to do it a little bit quicker because multiple processes can run on multiple processor cores. So we'll compile that. It compiles with no problem. All right, a couple of questions. First question, is this going to run faster, the same speed, or slower than the sequential version? Second question, is this going to produce the right answer or the wrong answer? And final question, is something going to go wrong? So figure out your answer to those questions, and now we'll give this a try. So we did in fact manage to go faster. It took about 0.6 seconds instead of 2.5 seconds, so that's a significant speed up, like a factor of 4 or a factor of 5 faster. Which makes sense. We have 10 processes running in parallel. We have 8 processor cores in this machine, so if we're able to get a factor of 4 speed up, that's not unreasonable. It's actually pretty good. It'd be nice if we could do better. If we're a little bit more careful about some of the complications, we could do better, but in this case, that's fine. The other question, though, is did we get the right answer? So the right answer is this value, and the answer that we got is this value, which is not quite the same number. In fact, the number that we got is a little bit smaller than the correct number. So that raises the question, why? Why did we get the wrong answer? So the answer to why we got the wrong answer is that we have the kind of bug that you always get when you have concurrent execution and shared memory. If you have concurrent execution and shared memory, you're going to have data races. And specifically, the problem is in this line of code right here. If we think about how this works in assembly, we can see that what's going on here is that this has to be 3 assembly statements or 3 machine instructions. First, we're going to have to move the value in memory pointed to by sum into some temporary register. Then we're going to have to add our II value into that temporary register. Then we're going to have to move the temporary register back into memory at the location pointed to by sum. So that's 3 steps. And the complication comes when we think about what happens when we have 2 processes. Let's say we have 2 processes that are doing separate portions of the range. Here I'm going to use 5 and 15 as the numbers rather than like 5 and 100 million and 5. But let's say that the initial value of sum was like 100, just arbitrarily. So now we have two processes that are adding these values in. And let's say that the way this ends up happening is that the instructions are effectively interleaved like this. Now we don't know how they're going to be interleaved. This is actually happening concurrently, and it's actually executing in parallel. So we actually can't even really specify a total order as to how the instructions are being ordered, but it matters quite a bit when we do these loads and stores to memory, what order those occur in. And so those that actually concretely happen in an order, because the memory chip itself is going to get requests to read and write data, and it's going to get those requests in some sequential order, because the memory address that both of these processors are accessing is the same memory address. It's the same physical 8 bytes of memory on some memory chip. So then our final instruction here is going to be mov from that temporary register, and this is a different temporary register in the second process from the first process, because every running process has its own set of registers. These are running actually in parallel, so they're running on separate processor cores, and so the two processor cores each have separate registers. So let's go through this. So we start with a sum of 100. We're going to load this into temp, so now temp is 100. Now we'll load sum into temp, so that's 100. Then we're going to add II to temp. Temp is now 100 plus 5 is 105. Here we'll add II to temp. Temp is now 100 plus 15, or 115. Then we're going to move the value in our temporary register for this process back into memory at sum. So sum is now 105. And now over in this process, we're going to move the value in its temporary register back into memory at sum. So now we've taken the result that we got is that 100 plus 5 plus 15 equals 115. That's a wrong answer. Not only is it a wrong answer, but it's wrong low. So we're adding a bunch of numbers together, and the result is a number that's smaller than the correct sum. And the reason for that is because we dropped the value 5 on the floor. We went ahead and did the arithmetic, adding 100 to 5. We got 105. We then stored that in memory, but then the other process immediately overwrote it without ever looking at it, because it had done the load before the first process had done its store. And that's what is causing our incorrect answer over here, is this data race. Alright, so the problem, or one core problem that is allowing this data race to happen is that what appears to be one simple statement in our C code is actually 3 instructions, so it doesn't necessarily execute atomically. Because it doesn't necessarily execute atomically, it can get split up in this way, and then the instructions from multiple processes can get interleaved. So we could solve this by forcing this instruction to execute atomically. All 3 instructions in one process need to start and finish before the 3 instructions in some other process that access the shared memory are allowed to start and finish. So let's go ahead and do that. We have a mechanism to do that called locks. So I'm going to write another version of this called locksum101.c. And in locksum101.c, we're going to add a lock. So we're going to allocate another thing in shared memory called lock. It's not going to be long though. It's going to be a semT. So then we're going to go ahead and unmap that. And we're going to unmap it in all the places that we unmapped our sum. I guess we want the lock to always be available while the sum is available, because that lock is going to protect this shared memory. And before we can use that lock, we're going to have to initialize it. And the way we're actually building a lock here, a lock is sort of a abstract synchronization idea. Concretely, what the operating system has given us is this mechanism called semaphores, which is a synchronization primitive provided by the operating system that can be used to build a lock. In order to turn this into a lock, we initialize it by calling seminit on the lock. We're just going to pass it 2 ones. And I may get into later why that gives us a lock, but for now, it gives us a lock. Now, a lock has 2 operations. The first operation is to lock the lock, and the second operation is to unlock the lock. Now, if we lock the lock and the lock hasn't been locked already, then the lock operation occurs, the lock is then in the locked state, and it will stay in the locked state until someone unlocks it. But if we attempt to lock the lock and the lock is already in that locked state, then instead of that lock operation completing, the process that is trying to lock the lock is going to block. It's going to stop executing at that line of code until it's allowed to continue. And it won't be allowed to continue until it can successfully lock the lock. And in order to do that, the lock has to be unlocked. So a second process attempting to lock a lock is just going to wait until someone unlocks the lock. According to the pattern, the first process, the one that got the lock, is going to unlock it when it's done, and that will cause the region between locking and unlocking to be executed atomically with respect to a piece of shared memory, as long as that piece of shared memory is only accessed while we're holding the lock. So the lock rules are so first, each piece of shared memory is associated with a lock. In this case, we have sum as our shared memory, and it's associated with that lock. So then the rule is that whenever the shared memory is accessed during concurrent execution, the lock must be in the locked state. Once we've done whatever atomic modification we want to do to our shared memory, we can go ahead and unlock the lock, and by we I mean the process that locked it does an atomic operation and then it unlocks it, and as long as we follow this pattern, we avoid this sort of data corruption problem of data races. At least in respect to stuff where the problem was that we wanted to do things atomically and we didn't. We still don't have a guarantee of what order things occur in, but if we think carefully about our program, we can avoid that being a problem. In this case, for example, we're doing addition, and addition is commutative, so it doesn't matter what order we do the additions in, as long as they all happen and they all happen atomically. So the way we spell lock with mutexes is, with semaphores, is we lock by doing sem wait on the lock, and then we're going to unlock by doing sem post on the lock. And so this is the lock operation. Multiple attempts to lock at the same time will block until that lock is unlocked. Let's give this a try. So that doesn't quite work because we need to include some more headers. we need semaphore. And this is still not going to work. Next problem is it's never heard of sem init or sem wait or sem post, and the reason for that is because semaphores are actually provided by libpthread. So we're going to have to link in libpthread when we do our linking together our object files into the executable. So once I add pthread to the end of that command, it will work. And now, same questions. Is this going to be faster than the parallel version, or the multiprocess version, the same speed as the multiprocess version, slower than the multiprocess version but faster than the sequential version, the same speed as the sequential version, or the slowest thing we've seen so far? And is this going to produce a right answer, a wrong answer, or a crash? Think about that for a second, and now let's give it a try. We run it, and it takes 4.0 seconds. So the sequential version took 2 seconds. So the version with locks is actually slower than just having a sequential program. And if we look here at user time, we can see that in terms of sort of CPU seconds, how much time was spent on processor cores, and if we're on 2 processor cores, that counts as time spent on 2 processor cores. It took like 7.5 seconds, compared to 2.5 seconds for the sequential version, or like 4 seconds for the initial multiprocess version. So locks do solve the problem of data races, but they lose our benefit of getting a parallel speedup, at least in this example. So in this example, like most of what we're doing, like 1% of our times through the loop, and pretty much 100% of the work that we do in the loop body involves taking a lock, modifying shared memory, and then freeing the lock. And so the operation of serializing this piece of the program effectively serializes all the work that we're doing, and so we don't get real benefits from running in multiple processes anymore. It's possible that if we have a bunch of processes that are working on like different pieces of memory and not having to take locks for all the work that they do, or not spending most of their time locking and unlocking locks, we could get a parallel speedup even if we're using locks, but locks are comparatively slow. Alright, so especially locks made out of semaphores, which is not necessarily the way we always do this. Alright, so that's one way to do it, but that didn't give us a speed up. Let's see if there's any other ways that we can do it. Now, if you think about this for a second, we can take advantage of the specific structure of this problem to try to make a version that will do the work in parallel without actually having data races. So think about that for a second. There's 2 or 3 ways to do this properly, but I'm going to go ahead and talk about one specific one. And I'm actually going to go back to proc sum 101 and turn this into par sum 101. So this is going to try to be a fast parallel version. So instead of having a single shared sum, I'm going to go ahead and allocate an array of 10 shared sums. And then we're going to, let me actually call this sums just so that we make sure that we don't have any like bad edit problems. Now, then we're going to go ahead and in each child, we're going to have a local sum variable. So we're not even going to do it in shared memory. So we're going to say long local sum is 0. Local sum plus equals ii. And then in the end here, we're going to say sums pp. So one particular slot in the global array that isn't going to be accessed by any of the other child processes is going to get a copy of our local sum. Now down here, we're going to have a long global sum, which is another variable back in the parent process. We're going to start that at 0. And then once a given child has terminated, we're going to say global sum plus equals sums pp, the shared sum. We'll go ahead and free that shared memory before we do our print. Then we're going to print out the global sum. Now this is a little bit more complicated logic than the previous versions, but the trick is, although we have shared memory, we've allocated shared memory as a way to communicate between processes, we never actually write to the same piece of memory concurrently. Each child gets its own item in the sum array to write to, and each one of those things is only written in one child. So no specific slot is actually treated as, is actually accessed by more than one process at the same time, so we don't have any data race there. And that may depend on the hardware, but in the case of an Intel architecture system, including AMD 64, we're allowed to have multiple processes access different slots in an array and not have data races. The processors will figure out the right answer. Then, once the child process has terminated, which means that we know that it's written its result out to the shared memory, we're going to read the sum from the shared memory in the parent process, and then we'll print out that final sum at the end. So let's give this a try. I meant sums, that's why we did this. And here. Trying this again. Alright, so we're going to time it. And this time we run slightly faster than the shared memory version, it looks like, or than the parallel version. The total CPU time is definitely faster, and we get the right answer. So by careful study of what we're actually trying to do, and avoiding the issues of the data that cause data races, specifically concurrent access to the same memory location, we can write a program that doesn't need locks and gets right answers. But let me give the punchline. A data race is possible if your program has shared memory, has multiple concurrent processes. So we don't just have to have shared memory. Shared memory is accessed concurrently by multiple processes. We have to have it be shared, and we have to use the fact that it's shared. And then finally, we have to have at least one process write. If we have, the parent process allocates an array, fills it with data, we spawn 10 child processes, and then they only ever read that data, we can't have a data race because we don't actually have concurrent writes. If we have one process writing and another process reading, that's potentially a data race. Even one process writing and several processes reading, we don't know what the order of the read and the write will be. So the read could happen before or after the write. That's a data race. But if there are no writes at all happening during the concurrent time of the program, we don't have a problem. So that's where we are. And we'll talk a little bit more about how locks can be a problem next lecture.